This is a video from section 12.2 and it's based off the lecture notes. If we place the initial point of a vector v at the origin, then the terminal point of v has coordinates of the form a sub 1, a sub 2, or a sub 1, a sub 2, a sub 3. This will depend on whether our coordinate system is in 2 dimensions or 3 dimensions. And we write v as the vector a1, a2, so that's right here. That's, again, if you're in 2D. Or we write v equals the vector a1, a2, a3, and I give you a visual representation of both. So notice in 2 dimensions, we start at the origin, and we extend out to the point a1, a2, and we draw an arrow once we hit the terminal point a1, a2. And in 3 dimensions, notice the x, y, and z axis. We start at the point 0, 0, 0. In other words, we start at the origin, and we draw, again, a line segment, if you will, until we get to the ordered triple a sub 1, a sub 2, a sub 3, and then we draw an arrow. And these give you visual representations of v, whether you're in 2D or in 3D. 2 vectors are equivalent as long as the vectors have the same magnitude. So in other words, the vectors have the same length and same direction. And if you notice, I draw 4 equivalent vectors in 2 dimensions. So notice here, I start at the origin. I go over 1 up 2 to get my terminal point P, and I draw the vector accordingly. Now, if I want an equivalent vector, let's suppose my initial point is 1, 0, and I'm going to go over 1 up 2, and I'm going to draw a vector here. And I claim this vector in blue is equivalent to the vector in red. And I could start at 2, 0, and I'm going to go over 1 up 2 to get my terminal point, and I can draw the vector accordingly. And so the vector in black is equivalent to the vector in blue and the vector in red. And then to cap things off, I went up to 0, 1, and then I went over 1 up 2 to get yet another vector that's equivalent to the other 3 vectors. And so all the vectors shown in the above figure are equivalent to v, which again is the vector 1, 2. So all 4 of those vectors are equivalent to the vector 1, 2. We can think of all these vectors as representations, it's another word, of the vector v, which is again equal to 1, 2. The particular representation OP from the origin to the point 1, 2 is called the position vector of the point P. So the position vector has the initial point start at the origin. And then we went out to the terminal point 1, 2. And OP is the position vector of V. In 3 dimensions, OP equals the vector a sub 1, a sub 2, a sub 3. This vector is the position vector of the point a1, a2, a3. Okay, so when I refer to this as the position vector, it is understood that the initial point is at the origin. Now, given points A, which is equal to x1, y1, z1, and B, which is equal to x2, y2, z2, the vector A with representation AB, right? So notice how I drew or I wrote AB with an arrow on top. So this is telling me my initial point is A and my terminal point is B. So now AB is equal to the following. To get the first component right here, I'm going to take x sub 2 and I'm going to subtract x sub 1. To get the second component, I'm going to take y sub 2 and I'm going to subtract y sub 1. To get the third component, that's right here, I'm going to take z sub 2 minus z sub 1. Okay? Now, remember, AB, that vector AB is different from the vector BA. So we want to be mindful of that. Now, let's take a look at an example. It says, find a vector A with representation given by the line segment AB. So now, notice how I have AB with an arrow on top, okay? Now, A, think terminal minus initial. To get the first component, I'm going to take negative 2. I'm going to subtract negative 1. To get the second component, I take 3, and I'm going to subtract negative 2. Now, if you guys just wrote negative 3 and 5, I can't argue with that very much. But remember, if you show me this and make an arithmetic error, that's worth more points. So just something to keep in mind. To get the third component, I take 0, and I'm going to subtract 4. And then from there, I'm going to get negative 3, 5, negative 4. And that's vector A. Again, think terminal minus initial. The length of A, which is equal to the vector A1, A2, is given by the magnitude of A, or the length of A, right? So notice how A is put in absolute value bars. That just means the length is equal to the square root of A1 squared plus A2 squared. Now, if we take a look at this, here's the y-axis, here's the x-axis. You can just think Pythagorean theorem. So I'm going to start at the origin, and I'm going to go out to the point A1, A2, like so. And I'm going to drop a perpendicular down. That's in blue. And so this side is A1. This side is A2. And the magnitude of A is the length of this vector here. And this is straight Pythagorean theorem. And we can make the same argument in 3 dimensions. So the length of A, which is equal to the vector A1, A2, A3, is given by the magnitude of A, or the length of A, is the square root of A1 squared plus A2 squared plus A3 squared. Okay? It's the same argument. What you're doing is you're going to apply the Pythagorean theorem twice. So here's X, here's Y, and here's Z, okay? And I'm going to start at the origin here, and I'm going to go out, okay? Remember, we're looking for this length. We don't know it. Now, this is A1, A2, A3, okay? And what I'm going to do is I'm going to drop a perpendicular down, okay? And I'm dropping it down to the xy plane, which means the z coordinate is going to turn into 0. And so this is going to be A1, A2, 0. And I'm going to draw a line out here, and believe it or not, this is a right angle. And we've already established the length of this side from above. That's just the Pythagorean theorem. So this is the square root of A1 squared plus A2 squared. Okay? And this length is A3. And if I apply the Pythagorean theorem again, I'm going to get this result right here. And that's how you would justify this second one. let's go on. If A is the vector A1, A2, and B is the vector B1, B2, then if we want A plus B, that's the vector A1, A2 plus the vector B1, B2. And I hope it's the way you expect. To add vectors, we're going to add corresponding components. So to get the first component of A plus B, that's going to be A1 plus B1. To get the second component of A plus B, we take A2 and then we add B2. So that's A2 plus B2. And by the way, I'm using 2 dimensions for these vector representations. We can make the same argument for 3 dimensions. What you cannot do is take a vector in 2 dimensions and add a vector in 3 dimensions. So we have to have the same number of components in order to add or subtract adequately. I hope that makes sense. Now, for number 2, we want A minus B. And so we're going to do this by components. And so we're going to get A1 minus B1 for the first component. And for the, And for the second component, we're going to get A2 minus B2. So that's how we subtract. If we want to take a scalar, so remember in context here, C is a scalar. We're going to take a scalar multiple of A. But that's C times the vector A1, A2. And we're going to take each component and multiply by C. So the first component is CA1. The second component is CA2. And so again, I want to stress a similar result will hold for 3-dimensional vectors. So we can do the same thing if we're in 3 dimensions. For example, if A is the vector 5, 3, and B is the vector -1, -2, we're going to look at A plus B. But that's the vector 5, 3 plus the vector -1, -2. So this is the following. To get the first component, I take 5 plus -1. To get the second component, I get 3 plus -2, like so. And so if I put all this together, I can say A plus B is equal to the vector 4, 1. That's it. Okay, now, suppose I want 4A plus 2B. This is what I would suggest you guys. I would figure out what 4A is first. What that essentially means is I'm going to take every component and multiply by 4. So 4A is 20, 12. 2B, right? So again, I want 4A plus 2B, so I need 2B. Well, that's going to be -2, -4. So therefore, if I want 4A plus 2B, this is 2012 plus -2, -4. So we did the hard work off to the side. Then we can add accordingly. And so this is 20 plus -2. That's my first component. My second component is 12 plus -4. Putting all this together, I get the vector 18, 8. That's how we do number 2. Number 3. suppose I want the length of A. And so I wanted to remind you guys what A and B are because I'm using them. Now remember, A is the vector 5, 3, and B is the vector -1, -2. So the vector A, the length of that vector is the length of vector 5, 3, which is the square root of 5 squared plus 3 squared. But 5 squared is 25, 3 squared is 9, 25 plus 9 is 34. So I'm going to write the square root of 34. And it's okay to leave it as the square root of 34. I don't need the decimal approximation. And so the length of A is the square root of 34. Now, we need the length of A minus B. Now, one thing to note here, and it's very important, the length of A minus B, or the magnitude of A minus B, is not the length of A minus the length of B. Somebody inevitably does that. Prove me wrong, don't prove me right. Okay? Now, A minus B, let's figure out what this is first. This is the vector with first component 5 minus -1, and second component 3 minus -2. Okay? And so this is the vector 6, 5. So therefore, if I want the length of A minus B, this is the length of 6, 5, which is the square root of 6 squared plus 5 squared. So again, we have to figure out what A minus B is before we can actually take its length. Now, 6 squared is 36, 5 squared is 25, 36 plus 25 is 61, and so we get the square root of 61. And so that's the length of A minus B. We get the square root of 61. Now, if A, B, and C are three-dimensional vectors and C and D are scalars, we have some properties. It turns out that A plus B is the same as B plus A. Think commutativity. Number 2, if I take A and add the quantity B plus C, that's the same as taking the quantity of A plus B and then adding C. Think associativity, okay, the associative property. On number 3, if I take A and add the 0 vector, I get A back. If I take A and then add -A, I get the 0 vector, right? Number 5, if I take the scalar C and multiply by the quantity A plus B, I get C times A, right? Plus C times B. If I take the quantity C plus D, this is number 6, and multiply by A, that's the same as CA plus DA. Number 7, if I take the quantity CD and multiply by A, that's the same as taking C and then multiplying by the quantity DA. Okay, so this is number 7. Number 8, if I take 1 and then multiply by A, I get A back. Now, one thing I want to make note of is in the book assumes that A, B, and C are three-dimensional vectors. Actually, I'm assuming they're three-dimensional vectors. The book assumes that the vectors are n-dimensional. That's fine when you're taking a linear algebra class. I'm really primarily focused on either the vectors being three-dimensional or two-dimensional. By the way, if the vectors are two-dimensional, all these properties still follow. Okay? So let me say that again. I'm assuming that these vectors are three-dimensional. The book assumes that the vectors are n-dimensional. What do I mean by n-dimensional? What I mean is n could be 5, n could be 100, n could be 1,000,000, n could be 2. Okay? N could be 50,000. So it could have A could be a vector with 50,000 components. Doesn't matter. These properties are going to follow. But because we're in Calculus 3, I'm really focused on two types of vectors, either two-dimensional vectors or three-dimensional vectors. That's it. If you're taking linear algebra, then we care about n-dimensional vectors a bit more in there. Okay, that's going to do it for this video for section 12.2. And this is, again, a video based off the lecture notes. Thank you.